I'm presenting a paper that I wrote together with Laurent Lehmann, who is also in the audience. And I'm very happy that he is, because this is really so we are perfect complements using standard terminology from economics, really complement each other. We're bringing things together that we could, I definitely could not have been doing alone, and maybe Laurent could not have done it alone either. So, and this paper was just published in a special issue, and it's the first time I present it. So one good thing, one nice thing I like about, special issues and that kind of, is that you tend to be able to publish very quickly something. And this was the case. So we were invited to contribute this paper to a special issue a bit over a year ago. And then now it's already published. So I like that, because then you can move along very fast. But on the other hand, that has also meant that I have not presented this one single time. So we got great feedback from reviewers, but I also really look forward to hearing your thoughts. And so I do believe that the presentation will be shorter than 1 hour, and so that will leave time for discussion. I also know that this audience is mixed, and that part of it does not, probably is not, not specialists of preference evolution. And so I will give a fairly long sort of introduction to this area. And now Laurent and we chose a very long title. I think this was not very strategic. It seems, all other things equal, it seems that papers with shorter titles are more cited. Anyway, so hopefully this will be a counterexample. Okay, so yes, of course, it will have escaped nobody, right? That this year marks the 50th anniversary of the birth of evolutionary game theory. So an evolutionary game is what? It's a mathematical description of a strategic interaction, namely a situation where one individual's strategy affects both own and someone else's fitness. And so the question of interest is, which strategy should evolution by natural selection give rise to? And so Maynard Smith and Price proposed the equilibrium concept of an evolutionarily stable strategy, or ESS for short, to analyze this question. So in an evolutionary game, right, so each individual is programmed to play a certain strategy. So if we think about our evolutionary past, what this, according to this view, evolution by natural selection should have equipped us with a kind of a huge recipe book, right? And this recipe book tells us what to do in every game that was played by our ancestors. We just need to recognize the game, and then poof, we play that strategy, ESS. For the past 15 years or so, part of my research has built on this work, and so does the paper that I'm presenting today. And so, as I said before, telling you about what exactly Laurent and I do, and also to explain our contributions, I will give you a fairly detailed background. So, given this interest in what people do in strategic interaction, coming from economics, as I do, I would have another take on this. So, I'm an economist by training, and in economics, the way we think about individual behavior is that individuals have preferences over the options they face. That is to say, so given any two options that an individual can choose between, two or more, of course, options, he either strictly prefers one of them or is indifferent between them. And he picks the one he prefers, and it's simple as that. Okay, so if we bring this idea to bear on strategic interactions, what will happen? So consider this material game here. It has two players, Lewis and Bob, two strategies, cooperate and defect, and the numbers in the matrix show the material payoffs. so the material payoffs that the players obtain for each strategy profile. And so this, as you will have recognized, this material game is a prism's dilemma. Okay. So now suppose that the payoffs represent the fitnesses of the individuals. Then, of course, we see and we know that defect is the unique ESS. So the prediction, let's say, from evolutionary biology is that people will defect in this interaction. Of course, as you know, given a bunch of assumptions, but let's stick with this uniform random matching and so forth, standard, a classic framework. Okay, so that's the prediction. Now, suppose that I let subjects in an experiment play this game. And suppose that I observe that Lewis defects, but Bob cooperates. And so as an economist, I would simply conclude that Lewis prefers to defect if Bob cooperates, and that Bob prefers to cooperate if Lewis defects. Oh, fine, but you may ask, but why would Bob prefer to cooperate? Well, then one can think of a host of explanations. It could be that Bob experiences guilt whenever he defects. So maybe he does care about material payoffs, but also he has experiences this guilt. And so imagine that this guilt is equivalent to 5 units of material payoff. And then clearly, with such guilt, Bob prefers to cooperate, whatever Lewis does. So Lewis, on the other hand, perhaps is a pure materialist. Maybe he simply wants to maximize his material payoff. And so now we have defined a non-cooperative game, and where the set of strategies are also cooperate and defect. The payoffs associated with each strategy profile are also indicated now in the cells. But so these are the payoffs and not the material payoffs. So the payoffs can also include any psychological costs or benefits from choosing this or that strategy, or from perhaps also deriving experiencing psychological cost or benefit from, let's say, reducing the inequality between the players, right? And so here, a Nash equilibrium in such a non-cooperative game, it consists of a pair of strategies such that so each player simply picks the strategy he prefers, given the strategy played by the other. And this here, it's picking the strategy with the highest payoff in the sense I just mentioned, given what the other player does. Okay, fine. So now what we're doing in this work is we're reconciling these two approaches, right? So how can this be done? And so then, just like in evolutionary game theory, suppose that individuals that are randomly matched and together, and they have play some interaction, which is given. I'll call that the material game. Right. And so just like in economics, we suppose that each individual also has some preferences. So here, the individuals are programmed with preferences. And the idea is that these preferences are inherited from the parents. And so each matched player, a pair of players, play some Nash equilibrium. And the strategies that are played determine the fitness of each individual. And so there we go. We have found a way to analyze how evolution by natural selection operates at the level of preferences. And so the goal here will be to determine what are the evolutionarily stable preferences. Yes, Peter.
Are you going to talk about what happens when there are multiple Nash equilibria?
We can talk about that later if you wish, for sure. But for now, yes. So models can encompass both situations, both when there are multiple or a single Nash equilibria. Yes. Okay. So here, let's say if we believe that this is the way that humans are shaped, then the predicted strategy that we should see in a population with evolutionarily stable preferences is some Nash equilibrium strategy, given these evolutionarily stable preferences. And so there's a large number of questions that can be addressed with this framework. For example, is the Nash equilibrium strategy, so yes, I mean, it could be multiple, but I'm sticking to the simple presentation mode here. Is the Nash equilibrium strategy under evolutionarily stable preferences, is that different from the evolutionarily stable strategy? If so, why? Also, can the evolutionarily stable preferences be given some kind of psychological interpretation? I mean, should we see guilt? Should we see some kind of inequity, aversion, altruism, or something else? What can we say about these preferences? And if we have that, we can actually also engage in conversation with psychologists and behavioral economists to study these preferences and seek to measure them even using experiments. So it's a very rich rich framework. So now, just a couple of more minutes of background before we get to the starting point of the paper with Laurent. So here's the thing: in the standard evolutionary game, selection operates at the level of strategies, right? And the set of strategies is really given by the material situation at hand. So for example, if it's a public goods game, then there could be a range of contribution levels, and that's simply given by the material situation. But under preference evolution, it's not that clear. So the material game does not dictate what the set of possible preferences is. And so as a modeler, we need to make some assumption about the set of possible preferences. And many different assumptions have been explored in the literature. And so this brings me to this paper, which is also kind of leads us to the starting point of the paper with Laurent. So in the paper that I published with Jürgen Webel 10 years ago now, we adopted the following approach. We posited a material game that is quite general. We have simply some strategy set X, and we make some assumptions about the mathematical properties of the strategy set. We have a material payoff function pi, which to each strategy profile associates a number. So this is also, it could be a public goods game, it could be a Princess Dilemma, it could be all sorts of material payoff functions. And in this paper, we assume that the set of possible preference types is the set of all continuous functions, where so such functions would associate to each strategy profile played by in each matched pair, associates a number. Okay, so what does this mean? For those of you in the audience who would not be familiar with preferences, I mean, before I talked about guilt and feeling guilty about defecting. That's quite clear. Here I'm talking now about simply a function that gives a number to each strategy profile. What do I mean by this? Well, it's quite simple. Again, whenever such a function gives a lower number to one strategy, say strategy A, than to another strategy, say strategy B, that means that the individual prefers strategy B to A. So a higher number simply indicates that it's a preferred strategy. Okay. In this paper, also, when you study a non-cooperative game theory, you need to specify what kind of information the players have about each other. So in this paper, we restricted attention to settings in which interactions take place under incomplete information, which means that each individual knows, of course, the own preferences, but here has no information about the opponent's preferences. Okay. In this paper, we also, as some other papers also in the 1970s, we included the idea that interacting individuals may be related to each other. But we took also the same kind of abstract approach as had been done in the 1970s to this by simply positing some exogenously given number between 0 and 1 and called that relatedness. And what this relatedness captures is the probability that a very rare mutant is matched with another rare mutant. Okay, so what did we find then with this exercise? What we found is that it's this particular function here representing preferences that stands out as being evolutionarily stable for all the interactions that we encompass in the model. So I'm not saying that this is the only evolutionarily stable preference function, but it is the only one that is stable for all the material games that we consider. Okay, and so now, so here we have these two terms, right? So we have the first term here, pi xy, is the material payoff that accrues to the players playing strategy X when the opponent plays strategy Y. So this is the individual's own material payoff. And this gets a weight of 1 minus R, where R is relatedness. And the second term here takes relatedness times this term here, pi of XX, which is the material payoff that the individual would get if both individuals were to play X, that is the strategy that the individual himself is playing. Okay, so this was actually the math that led us to this function, and so we looked at it and we thought of Immanuel Kant when we saw this expression. So Immanuel Kant would say one should act only in accordance with that maxim through which you can at the same time will that it become a universal law. And so we looked at this, and the second term reminded us of Kant, but we can then express this as one should select a strategy that one can at the same time will that it be selected by the opponent with probability R. And so this is where we can call these preferences semi-Kantian preferences. In the paper, we call them homomoralis preferences, but the word semi-Kantian had already been used also by Ted Bergstrom when he analyzed strategy evolution with relatedness in the 1990s. And so this brings us to the paper with Laurent and why we take interest in this class of preferences. Before talking about the paper this paper, let me just also mention that together with Laurent and Jürgen and I, we embedded, let's say, this framework that we had developed in 2013. And thanks to Laurent, so we incorporated this into an island model. And to what this, on the one hand, does is that it makes relatedness endogenous. And so it brings the model closer to standard evolutionary biology models. And so in this model, we have that individuals are equipped with preferences, and these preferences guide the strategy choices. But now there is an additional layer compared to the 2013 paper, which is that there are material payoffs generated by these strategy choices. For example, those could be calories or wealth or something like that, and could be small in view of the whole life and reproductive success. And these material payoffs in turn determine the biological fitness. But we again took the set of preference types to be the set of all continuous functions as before, and we also let interactions take place under incomplete information. Okay, so what is new here is that we have the island model, which makes relatedness endogenous, and we can also make this distinction between material payoff and fitness. Okay. And so this brings us finally at long last to today's paper. So what we do today is we still have, let's say, an idle model, and where relatedness is endogenous and depends on life cycle events. We also have that preferences give rise to strategy choices. And we don't talk so much here about the material payoffs, we go directly to fitness. And we take here, instead of taking the set of possible preferences to be the set of all continuous functions, we here just posit this class of semi-Kantian preferences that have been shown to be favored in this previous work as being favored by evolution by natural selection. And so a preference type here would be consist of the weight attached to the Kantian term. And what we do, what is novel here is that we examine 3 different information scenarios, including the incomplete information that we just talked about. And what we also we'll try to push the analysis a step further also in a way that I will tell you about. Okay, and as I said, this was just published in Dynamic Games and Application in the special issue. Okay, any questions on this background? Okay, so what is the setup? Setup is that we have a population that is divided into an infinite number of groups, and each group has 2 adults. And so in each demographic time period, each pair interacts. They play in Nash equilibrium. Yes, so each individual produces a large number of juveniles, and then and may then die with some probability. Each juvenile migrates to another group with probability m, or otherwise stays in the natal group. And so in each group, you have a number of candidate juveniles that are trying to get a spot that is freed up by an adult who has died. So the available spots are filled up by the competing juveniles, probabilistically, so with equal probability for each juvenile. And those who succeed in getting a spot, they become adult. And so that closes the demographic time period. So here, the personal fitness of an individual depends on own strategy, X, on the opponent's strategy, Y, but also on the strategy, I'll call it here Y star, played in the population at large, in the other islands. Okay. And so given this personal fitness, so now we have the material game, and so here are the semi-Kantian preferences in this setup. So it's a function that to the strategies X, Y, and Y star associates a number. And this number is the sum of these 2 terms. So first we have 1 minus theta, and theta is a number between 0 and 1, simply. And here's the it's the own personal fitness of this individual who plays X when the opponent plays Y, and the strategy played in the population at large is Y star. And here's the second term is the Kantian term. So we still have this Y star playing the population at large, but now the individual calculates, let's say, what his fitness would be if not only he, but also his opponent were to play strategy X. And he attaches the weight theta to this Kantian term. Okay, and so the thought experiment is the following. There is a resident type theta, and suddenly there is a mutant type that appears in exactly one individual. And so we use what is called standard invasion analysis, which consists in doing the following. It looks at what is called invasion fitness. And this is the expected individual fitness of all the descendants of the initial single mutant. And so the notation here will be this capital W, and that was a function directly of the two types, the mutant type and the resident type. The first term here, this squiggly W index 1, means that is the personal fitness of a mutant when there is only one mutant in the group. So when a mutant is matched with a resident. Squiggly 2 here, squiggly W2, is the fitness of a mutant when there are two mutants in the group. So when a mutant is matched with a mutant. Okay. And R here is relatedness. And as I mentioned, this relatedness is typically depends on both the, generally speaking, depends on both the resident type and the mutant type. And depends on the life cycle events in the demographic time period. Okay. Any questions?
I have a question about the population at large. So this doesn't seem to matter for invasion fitness, or this is for a given.
It does matter. So what the mutants, what the residents in the population at large do does matter. So it will show up. I will show you later the full expressions. But indeed, I mean, for here, for example, you can see that even when two mutants interact, it depends on theta, the resident type, because the resident type is the strategy being played in the population at large.
Right. So the squiggly W, should I imagine this as also a function of three variables? But
absolutely. So I will show you. So squiggly W is just indeed. So I will show you later exactly what these squiggly W's are. W as a function of the equilibrium strategies. Yeah.
I'll let you get to it.
Okay. Okay. So and so to identify, so the resident type theta will resist the invasion of this mutant type if and only if this expression is smaller than 1, which is equal to the fitness of residents. Okay, in this constant population model, the fitness of residents, given that the resident trait is carried by essentially the whole population, is 1. So when one looks at a set of possible values for these mutant types and resident types, what is really handy is when this W function is differentiable in the mutant type. But in any event, what one wants to identify is a resident type theta that such that there exists no tau such that W tau of theta exceeds W of theta theta, so that the W, we can think of W tau as being a function of tau, and so this should reach a maximum for tau equal to theta. That's when you have a candidate for an uninvadable, well, that's when you have an uninvadable type. So when W is differentiable, then one looks at the selection gradient first to identify candidates. So those values of theta that satisfy the first order condition for a maximum to be reached at tau equal to theta. And then here's the second order condition, looking at the Hessian then, that indeed it is a maximum rather than a minimum. And if so, any trait type theta star that satisfies these two conditions is uninvadable. Okay, so this is also what we, how far we push the analysis in the paper that I mentioned previously. So what we're doing here is we're pushing one step further also is to look at convergence stability. So the question is, would we ever get to, even if we have if we identify a trait that satisfies these two conditions, the question is whether evolution would ever bring the population to this state gradually. And so a convergence stability, so theta star is convergence stable if it is satisfies this first order condition, and if moreover here the so you take a population with some resident trait theta close to theta star, and then a selection should then bring the population towards the trait theta star. If that's the case, then theta star is convergence stable. Okay. And so the goal of the paper is to identify uninvadable and convergence stable semi-Kantian preferences, so the value of this weight on the Kantian term on the three different scenarios. Incomplete information, so interacting individuals do not observe each other's type. They have correct beliefs about the distributions they face. Then we look at complete information and incomplete plasticity. Interacting individuals observe each other's type, but they have also always the same preferences. So an individual's weight on the Kantian term does not depend on the opponent's type. And then we have complete information and complete plasticity. So complete plasticity means that now an individual's weight on the Kantian term can also depend on the opponent's type. So an individual can have a bit schizophrenic, have one preference when interacting with one particular type and another preference when interacting with another type. Okay. Good. So that's the goal. Let's see now how far we could push this, given the time constraint that we had. So under incomplete information. So now, Peter, here's the information that you were looking for. So the invasion fitness here, the first term is the personal fitness of, this is a X star tau theta. Here is the equilibrium strategy of a mutant. And Y star theta is the equilibrium, the strategy played by residents in the population at large. They interact with each other. However, because of incomplete information and because there is only a finite number of mutants in this infinitely large population, that means that the residents play the same strategy whether they interact with a mutant or a resident. Okay, and this is an important feature here of but the key feature of the incomplete information scenario is that here the resident does not budge. Okay, always plays Y star of theta. All right. So yeah, the Nash equilibrium strategies are implicitly defined by these first order conditions here. We make, we adopt the assumptions that are sufficient for us to be able to restrict attention to interior solutions. And we assume that in this paper, we assume that there is a unique Nash equilibrium just to make things simple. And so the selection gradient looks like this, because the y star does not depend on tau. The only effect of a change in the value of the mutant trait is that it changes the mutant's own strategy. And it then affects the mutant's fitness through these two terms. Now we can, thanks to this first order condition here, we can rewrite the selection gradient in this way. And this second term here is strictly positive. And so we have then identified the value of the sole unique value of theta that is a candidate for an uninvadable strategy, namely theta equal to R. And in this setting, it's also, yes, Peter?
Oh, can you go back one? So
Yeah.
here, and I know I'm too slow for these, but here there are two games. On the top line, we have W x star, y star, y star, and W x star, y star. So
Right.
X star is the Nash equilibrium that I play when I'm matched with a resident and when I'm matched with a mutant. And I'm wondering
exactly. So here the incomplete information. So you don't you do not observe your opponent's preference type here. So you do not know whether you're matched with a resident or with a mutant.
That's right. And
so here the notation indeed is x star tau theta. The notation is that it is the equilibrium strategy of mutants with type tau, given that the resident type is theta. And why does it show up here? It shows up because as you can see, so here we have the second line here is the first order condition that defines x star tau of theta. And because y star appears here, then x star depends not only on tau, but also on theta.
Right. So that defines my x star, and I might just be so unlucky that this is not a Nash equilibrium in either of these cases. It's just the best response.
Absolutely, it could be. Yes, that's right. It could be that there's some other strategy that would be a best response if I could observe the type of my opponent. Yes, indeed.
Thanks, I caught up.
Okay, so in this setting, which turns out to be straightforward, right, in terms of thanks to this non-reaction by the resonance, we can get easily the expressions for the Jacobian and the Hessian so as to actually say something quite precise about whether this theta star is uninvadable and or convergent stable. So this is the result. When interactions take place under incomplete information, the counting coefficient equal to the relatedness is a unique singular trait value. It is both convergent stable and locally uninvadable if relatedness is not too sensitive to the trait values. So for convergent stability, the condition, the necessary and sufficient condition for theta star to be convergent stable is that this thing here be strictly negative. So here we have the condition. And it's locally uninvadable. So we know that the K here, this whole term here is strictly negative. The K is strictly negative. And so a sufficient condition is that this also be negative, or at least that it not be too large. So that in particular, if, for example, if relatedness does not depend on the trait value, then this theta star would also be locally uninvadable. But so it depends, it simply depends on the kind of interaction. Okay. Okay, so this kind of confirms what we knew from before, but it also adds this result on convergent stability, which is nice. Okay. Going now to complete information and incomplete plasticity. So the invasion fitness now, here we see that here the complete information, so the interactants observe each other's preferences, meaning that the residents in the population at large, when they interact with each other, they play the Y star of theta and theta, okay, the two types in own type and opponent's type. When a resident interacts with a mutant, the Y star may differ from what it plays when it plays against a resident. So, and the same is true for a mutant. The mutant may play differently when matched with a resident than when matched with a mutant. And the key thing here is really, this is what I'm going to drive also of the result here. The key thing is to what extent a mutant coming into a population can make the resident change its behavior, right? It can, for example, think about a public goods game and think that initially the resident trait is such that you have a certain contribution level, and consider now a mutant type that is less Kantian, okay, has a lower, the tau is smaller than theta. So such a mutant will contribute less in the public good, to the public good. Now, if the public goods game has strategic substitutes, then that means that the resident, when interacting with a mutant, would actually contribute more than when interacting with another resident. So, and of course, the mutant benefits from this, right? So the observability of preferences makes the let's say the commitment of a mutant to contributing less credible. It just simply acts on its preferences, and this is written on the forehead of the person. And so the resident reacts and say, "Ooh, here comes a person who is not so moral, and so I will contribute more because I am quite moral, and so I will compensate by contributing more." All right. So here we have all these first order conditions, then defining the Nash equilibrium strategies and the different kinds of pairs. But so what really matters then is the reactions of both the mutant and the resident to the value of the mutant trait. So before we had this, of course, we had that the mutant himself would react to value of tau, but now we have also this additional term appearing in the selection gradient. And what we can do is, again, we can use the first order conditions from the behavior, so to simplify the expression of the selection gradient. So we can write it this way. And here, so here we have two terms. This is positive, this is also positive. And so identifying a candidate for an uninvadable value of theta now boils down to identifying values of theta for which this is 0. A rho here is this response coefficient. So it's the ratio of the mutant trait values effect on the resident over the mutant value, and so the value of the mutant trait effect on the mutant's equilibrium strategy. Okay, so yeah, selection gradient is 0 if and only if this is true. Okay, so now we see also a connection with the incomplete information scenario, because if rho is 0, so if actually for some reason, you know, and this happens when in certain games where the strategies are strategically neutral, then rho is 0, and then we are back to the incomplete information scenario, and that's not so strange, right? Incomplete information means the residents do not change their behavior when mutants appear. But things here are different when residents do change their equilibrium behavior as a response to a change in time. Okay, so strategies are strategic substitutes. If this rho is negative, then the behavioral responses go in opposite directions. The strategic complements if it's positive, and strategically neutral if it's 0. And so here's the result that we can show. So let theta star denote a singularity. So we want to say something about, you know, what are the singularities. So let theta tilde be a solution to this equation that I just showed you. Okay, then so in the cases where this solution here would be negative, then theta star is 0, because we restrict attention to values of theta between 0 and 1. But if theta, this theta tilde, if it's a value between 0 and 1, then that's the singular trait value. Okay. And so we can say something about whether this trait value is equal to relatedness as under incomplete information, and that is the case if strategies are strategically neutral. If it's below R, that is the case if strategies are strategic substitutes, or above it, and that's the case when the strategies are strategic complements. Okay. However, due to the complexity of the expressions that you saw, we were not able to determine in general whether this candidate value of theta, if that's uninvadable. So we cannot in general say much about the second order condition for a maximum. And we cannot say much in general either about convergent stability, unfortunately. So, but we have some numerical examples in the paper if you're interested. And I think that also this is something where you know, the time constraint may have also hit us here, in the sense that we could not really spend a lot of time thinking about whether we could see patterns and say something more general. So. Okay. Any questions before I go on to complete plasticity? All right, so complete plasticity. All right, now we have, I will not show you the first order conditions for the equilibrium strategies, but those are very similar to the ones you have seen before. What's important to notice here is that whenever, so here, first of all, a type is a vector. Okay, it's 2 numbers. So a resident type has now a theta d and a theta s. The theta d, so a resident applies theta d when interacting with someone whose type is different, either on one or both vector components. And a resident applies the value theta s when interacting with someone who has the same type in both dimensions. Okay, so in particular then, if the mutant is identical, has the same type, if the mutant type is the same as the resident type, then they simply, both residents and mutants simply play the same equilibrium strategy. And so the mutants here would have a chance to invade only if they have when anything is going on, only if the mutants have a different type than the residents. And so here, so the strategy being played at large is a natural equilibrium strategy between two residents having, and when they apply the theta S part of their type. But here the resident equilibrium strategy when playing against a mutant, it does depend on theta S because of what is playing in the population at large. However, let's say immediately in their interaction, the resident then applies theta D. And the mutant applies tau D when interacting with a resident, but it applies tau S when interacting with another mutant. Okay. Right. So that's what matters here is this. So it took us a while to see clearly what was going on here. So and also to kind of figure out how to write the paper about this, because what happens is that, so there are generically multiple candidates for uninvadable types, and we do not have differentiability anymore, because whenever the residence type, so the resident switches behavior when and it can switch behavior in a discrete way, right? Depending on whether it interacts with a resident or a mutant. So invasion fitness is no longer differentiable in tau, because tau would reach the resident value, it may jump in a discrete manner. So typically, there are multiple and unevadable types. But here's a safe bet. Let's say here is a type that always works. Whatever the game that you consider, this type always works. It is such that a resident applies a theta equal to 1, but it's a fully Kantian when interacting with another resident. And so what this means also is that they are then maximizing their joint fitnesses, right? And then the resident applies theta D equal to the value theta that is uninvadable under complete information and incomplete plasticity. That's the best theta to play to use, let's say, to prevent the invasion by a mutant type. So the resident type is kind of an angel towards other residents, but devil against anyone who shows up and who has a different type. So to some extent, this reminded us of your secret handshake paper, Arthur, in the sense that here we have this, right? I would fully cooperate with an individual who has the same type, but play something quite less Kantian when cooperating, when playing against someone who doesn't have the same trait. Okay, I will not go into more details. I welcome you to look at the paper for nice figures. Of course, all of that is produced by Laurent. I'm completely unable to produce graphs and examples and stuff like that. So there are some nice numerical examples. So it is, it's this discrete jump. So what happens is that here, a mutant always gets a strictly lower, so the invasion fitness here is also always strictly lower than 1. That we can show in general. So it never approaches 1, and that's why it gives flexibility. There are degrees of freedom such that the resident could typically deviate slightly from one here, have a slightly lower theta S, and so forth, without being threatened. Okay, so yeah, I'm essentially done. So I think that human beings are not ChatGPT-like robots. We are not programmed with a detailed recipe book of ESSs. We have the ability to reason. We act on information about the interaction at hand and also information about the interaction partners. And humans are able to select the strategy that they prefer. And we can study this using preference evolution models. And so in this paper with Laurent, we examine semi-Kantian preferences, known from previous work to be favored by evolution by natural selection. We explore 3 information scenarios, one of which is completely new to the literature. And we analyze both uninvadability and convoluted stability. And there are a host of questions that remain to be explored. If you're interested, if you don't know this literature, there are a couple of recent surveys that you can read. One of which was written more for having in mind an economics audience, and the other for more biology audience. And yeah, thank you.
So